Okay, questions. The first part of chapter 12 is now we're going to take double bonds and we're going to add things to it. So the first set of reagents that we're going to add is H plus along with a halogen. So in other words, like HCl or HBr or HI. And then the other one is H plus and an alcohol. So, were there any questions about that? Sure, let's do a practice problem. Practice problem number 1. Let's go ahead and add HCl to that alkene. And so what would be the major product of that reaction? Well, that's what you have the little whiteboards for. So you can write the product, so you can write the major product of that reaction and then hold it up. And if you're in the back, make sure that your ring takes up most of the whiteboard so that I can read it. Does everybody have one? Okay. So you can discuss. I'll give you a minute or so.
Looks all lopsided.
It doesn't matter. It doesn't have to be perfect. Just has to be the major product. Yeah.
You're like, perfect.
I want to take a look at that one again.
You also have a really nice handwriting.
I've been doing this a long time. When you get an answer, you can go ahead and hold yours up and I can... Okay. Look at that one again. Okay. Just because I say okay doesn't necessarily mean it's correct. It just means I'm acknowledging that you're writing something. Okay. Unless I say look at it again. Look at that one again. Okay. You might want to look at that one again. Okay. Okay, have I seen everybody's? All right. Is it the bottom one? Okay. Okay, so we got two issues here. Does anybody else want to show me? Okay, so here's the issue. The issue is for the reactions that we're going to do in this chapter, the alkene additions, we're going to end up for each reagent adding 2 things to the double bond. So the first thing for every reagent you need to know is, what am I adding? So in this case, what am I adding to the double bond? I'm adding an H and a Cl. Now, in this case, there's 2 ways to add the H and the Cl. So let's go to the mechanism. So I have an H plus and a Cl minus. What is the double bond? Is it an electrophile or is it a nucleophile? The double bond. Electrophile or nucleophile? Nucleophile? Okay, and what's its source of electron richness? The pi bond of the double bond is what makes it electron rich. Okay, so what is it going to react with, H plus or Cl minus? H plus, okay, because it's electron poor. So here's what's going to happen. I'm going to take this double bond. I have, let's call this carbon A and B. So I have 2 possibilities here. I can take this double bond and bond it to H plus. I can put the hydrogen I could attach to carbon A, or I could attach the hydrogen to carbon B. And then what happens to the other carbon that was in the double bond? It becomes a carbocation, because basically, in order to bond the hydrogen to A, I had to take the electron away from B. So there's a plus charge here, and then there would be a plus charge there. So this is if I add the H to A, this is if I add the H to B. Now, which one of those 2 carbocations is the most stable? A or B? Write it on the board. Which one is more stable, A or B? Okay. Okay, so I see a majority Bs. Why would B be more stable than A? Because it's a tertiary carbocation. What kind of carbocation is A? Secondary. So then the B is going to be the most stable carbocation. Okay. Now, in these kinds of, each reaction is going to have its own rules. But whenever you add an electrophile to the double bond and follow that up with a nucleophile, you'll always form the major product from the most stable carbocation. Okay. So in this case, the second step of the reaction is to take the chloride, have it react with the carbocation, to then have the H and the Cl, and have the chloride come in and react with the tertiary carbocation to then have the H and the Cl added in that fashion. And so there would be my 2 products, A and B. So whenever we do an addition reaction to a double bond, which is what we're going to be doing for at least the next week or so, probably up till Thanksgiving and after, you always have to know, what am I adding to the double bond? What 2 groups am I adding? And in this case, it's H and it's X. Okay. So that's the first thing we need to know, because there's going to be 3 things we need to know about every alkene reaction that we do. And question number 1 is going to be, what am I adding? So HCl, I'm adding an H and a Cl. And that's what I did. I added H and Cl. Okay. Now, I added in both directions. Right? I added H and Cl and then vice versa. And we'll have to know the rules of what would be the major product. And in this case, the major product comes from the more stable carbocation, which is the tertiary one. Now, the second thing that we need to know for every reaction is, how are those groups adding? And it was known that the hydrogen, when you add HCl to a double bond, it was known that the hydrogen would add to the carbon with the most hydrogens before the mechanism was ever known. That was the pattern that we had. So if we took a whole bunch of alkenes and added HCl to them, we would always find that the major product, the hydrogen added to the carbon with the most hydrogens. And that is what is called Markovnikov's rule. The Markovnikov rule says that you add the hydrogen to the carbon in the carbon-carbon double bond that has the most hydrogens. And that will give you the major product of the reaction. So Markovnikov's rule allows us to predict what the major product would be. In the reaction we just did, carbon B had one hydrogen attached to it, carbon A had 0. So that means that the major product we would predict would be the one where the hydrogen is added to the carbon with the most hydrogens. And that is what is called Markovnikov addition. Okay, because it follows Markovnikov's rule. Okay. So, what am I adding? HCl. How am I adding it? I'm adding it by Markovnikov addition, because I'm following Markovnikov's rule. Okay. So that was question number 2. It's questionable as to whether Markovnikov should get credit for this, because his paper doesn't necessarily talk about this at all. He just somehow in the early 1900s, his name got associated with it. There's people that would like to remove his name, because they're like, well, he's getting credit for something he didn't do, I guess. But we're since every organic book still has Markovnikov in it, we're going to keep it there. So Markovnikov was Russian, but the paper is in German, I believe. So a few years ago, we had a visitor whose wife was taught in physics, and she was from Germany, and she was helping a student translate that paper at a university in Minnesota. And he's like, do you realize he didn't do any of this stuff? And I go, I don't have time to figure out the history of a lot of this stuff. But then we looked at it, and it's like, yeah, he really didn't do any. He didn't really do this. But yet somehow it's associated with the name, because I have like a late 1800s organic book, and there's no Markovnikov addition. There's no addition to alkenes, period. So sometime between 1900 and the 50s, it got associated with him. Probably in the 30s. But I digress. That's his name is associated with it. We're going to. I don't know if Zaitsev, if he should get credit or not, but we're still going to associate his name. So Markovnikov addition means hydrogen adds to the carbon with the most hydrogens. What if they both have the same number of hydrogens? Then you're going to get 50-50. What if it adds opposite, which it will? Then we call those anti-Markovnikov additions. And we'll do some of those on Friday. Okay, so what am I adding? How am I adding it? So what am I adding? How am I adding? Markovnikov, anti-Markovnikov. Okay. Right. So third question, which I will use this. I will use this reaction. The third question is, well, let's see. Question number 1, what am I adding? Question number 2, how am I adding it? Or how are they added? Question 3, how are they added? Question 2, Markovnikov addition. Question 3, how are they added? Are the groups added 100% cis? Are they added 100% trans? Are they added 50-50? Or are they added some random amount? So in this case, it doesn't matter whether you add the H to the top or bottom carbon or the chlorine to the top or bottom carbon, you're going to get the same product. What I'm interested in here is, how am I going to add those hydrogens? Or am I going to add the hydrogen and chlorine? 100% cis, 100% trans, 50-50, or just random? Okay, so think about that for a minute. You can discuss if you'd like. There is no, well, you know what? If you're going to write the letter on there, there is an E possibility. The E possibility will be don't know. Discuss for a minute, and then I'll ask you to write your letter down and then hold it up. Are you ready to vote? Okay, so write down your letter A, B, C, D, E, and hold up your card, or hold up your thing. Okay, I see mostly, I see C's, and then I see a C/E. Nobody's going for random, because if it's random, we just move on. It's not. So C 50-50. Y 50-50.
You said like in like one of the videos that like the very end of the mechanism was like SN1, so or something like that. So it made sense that like you'd have like a 50-50. Like kind of like the racemic factor.
Okay. Anybody want to propose another explanation? Man, if I said it in the video, it has to be correct. First step in the mechanism is to do what? Add H plus to a double bond. Which double bond? Which carbon in the double bond do you want to add to, top or bottom? Give me one. Top. Okay, you want to add it from above the plane of the ring or below the plane of the ring? Above. Okay. Okay, I just added the hydrogen above the plane of the ring to the top carbon. That's going to leave the carbocation below. All right, where's the chloride going to add? Sorry, where's the chloride going to add to the carbocation? Below? Well, it does matter. That's different than it doesn't matter.
Oh, okay. It can attack from either direction.
Yeah, either direction is different than it doesn't matter. Because it does matter. So, yes, I didn't say in the last reaction, but if I go back there, I didn't say what this second step looked like. the first step is new, right? First step of adding an electrophile to a double bond is new. But adding a nucleophile to a carbocation is not new, because that is SN1. So the second step in this is SN1. So when we look at this, we say, well, the chloride's going to add to the carbocation. What did we learn in SN1? It would add 50-50. So it would add 50% from above the plane. It would add 50% from below the plane. Why? Because the p orbital of the empty p orbital of that carbocation is both pointing towards you in front of the screen and pointing away from you behind the screen, the way I've drawn it. If you don't like that, we could write a flat cyclohexane on its edge, and we could say, well, we added the hydrogen here, the methyl group is there, but then there is my carbocation with my CH3 here. And so where will the chloride add? 50% from the top, 50% from the bottom. Now, if you're saying, but wait, what about the influence of whether the hydrogen or the methyl group is here on the chloride? Will that affect where the chloride adds? So maybe you say, well, the methyl group's below the plane of the ring, won't the chloride add above preferentially? Or maybe the hydrogen's above the plane of the ring. Does that play a role? Let's just say for the sake of argument it did. Let's say the chloride somehow preferentially is going to add from the top because the methyl group is playing a steric role. Why did I add the hydrogen to the top? To begin with, why did I add the H plus to the top carbon? Because you told me to. Because you told me, I said top or bottom, and you said top. What if you would have said bottom? I would have added it to the bottom, and where would the methyl group be? On the top, so where would the chloride go? Chloride would, if the methyl group is affecting the chloride, it would go in the opposite direction. Or if it's affecting it positively, it would go in the top direction. So in other words, even if that was the case, which is kind of unlikely, but possible, I had the hydrogen's going to add 50% to the top and the bottom when it initially adds to the double bond. So that means I'm still going to end up with a 50-50 addition of H and Cl. 50% cis, 50% trans. And the addition to that carbocation is SN1. So if this was a single chiral center, you would get a racemic mixture. You would get both R and S, 50-50. Okay. Does that make sense? Because I'm going to broaden this out and say anytime any of these mechanisms that we do where we're adding things to double bonds, if it goes through a carbocation intermediate, it's going to be 50-50 cis-trans. Automatically. Because that second step is essentially SN1. And there's no preference of adding top or bottom. Or as we saw, if you want to argue there's a preference, the initial addition is going to cancel that out. It could be below. It's your choice. It's your choice. The reality is neither of these is going to affect the chloride that much, if at all. I'm probably giving it more credit than it is. It's not going to affect it at all. So the chloride's going to add 50-50. Okay, so everybody okay? So we're going to be making, well, at the end of this, we'll have a long table of reagents, because we'll probably have a dozen reactions when we're all said and done. Everyone with its different set of rules, each one with its own intermediate, each one with a mechanism that we may or may not have to write. Some mechanisms I'll show you to show why they go a particular way, whether Markovnikov, anti-Markovnikov, or cis or trans. But we're going to have to know those three things for every reaction. So what am I adding? HCl. How am I adding it? Markovnikov. How am I adding it? 50-50 cis trans. Okay. And so for every reaction, we're going to have those three columns that we have to figure out.
This might be kind of a dumb question, but I'm kind of confused on what you mean by cis and trans exactly. Like, is it cis to the ring? What's it cis and trans?
Okay, so here are my two possible ways. So I know I'm adding an H and a Cl to the double bond, right? So I'm going to add an H and a Cl there, and I've got two methyl groups here. So let me do that over here as well. In this case, it didn't matter whether I added the methyl group to the top, or sorry, the hydrogen and the chlorine to the top or the bottom, or both. Both, because I'm going to get the same product because the two methyl groups are the same. But what's the orientation of the hydrogen and the chlorine at the end? That's what I'm talking about. So either the hydrogen and the chlorine are both cis, or the hydrogen and the chlorine are trans. Which also means that the methyl groups are either cis or trans. So that's what I mean by cis or trans. Because if you think about this in terms of the reaction, if I have a double bond that I'm going to add two things to, I can add them one way, top and bottom. Okay, that's Markovnikov, anti-Markovnikov. I can add them cis, or I can add them trans. And so that gives us the potential of four different products. Right? If adding top and bottom and then switching the groups makes a difference, I could end up with four different products. Markovnikov versus anti-Markovnikov, 100% cis versus 100% trans. So I'm always going to be looking at the possible products, but for some reactions, it's only going to give one combination. So in this case, anytime you have a carbocation, it's going to give you 50-50 cis trans. So this product would be exactly 50% and 50%. So those are the three things we have to look out for every reaction. So this HX, no matter what X is, whether it's a chloride, bromide, iodide, it's always going to add Markovnikov, and it's always going to add 50-50. Why? Because it goes through a carbocation intermediate. Okay. On Friday. I don't think there were any anti-Markovnikovs in the reading for today. So Friday's readings start, because we're not doing an entire chapter at a time now. We're back to our regular schedule, so it's like, I don't know, half a chapter at a time. But it's still not an entire chapter at a time. So in this case, we're doing Friday, we're going to do some anti-Markov. We're going to do some Markovnikov and some anti-Markovnikovs.
Can we do one with an alcohol?
Sure. So then I would say, Let's do one where we make an alcohol. So I give you this reaction and I say, write the major product of this reaction. And I also say, write the major product of this reaction without rearrangement. Okay. So, take a minute and draw the structure of the major product of this reaction without rearrangement. What would it look like? And if you're thinking, well, I need just a little bit of a mechanism to get me by here or get me started, what's the double bond going to do? React with the H+. Markovnikovly. And then what do you form? Carbocation, and then what happens next? Then it's like an SN1 reaction. Okay. 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 And then when you figure it out without rearrangement, what would be the product with rearrangement? Okay. 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 Okay, maybe Markovnikov. Think about Markovnikov. We want the Markovnikov, and we don't want the rearranged one yet. We want the Markovnikov. Okay? Okay. We want addition, we want substitution with the carbocation, not elimination. Okay. Okay, okay. Okay. Okay, okay, okay. Okay, okay. Okay. Yep. Is that, which one is that? Okay. That might be the second one. That one is first one or second one? Okay. Okay. First one or second one? Emily. Okay. 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 We want Markovnikov. So remember Markovnikov, H always goes to the carbon with the most hydrogens. That's number 1 or 2? 2, okay. 2, 2, 2. Okay. It's number 1. Okay. Point where the OH is. I think you've moved one place too many. Okay? Number 1? Okay. Okay. Number 2?
Yeah.
Okay. You might have gone 1 carbon too far. Like on the bottom. So start out with your original carbocation and then rearrange it. But remember, you're only allowed to go 1 place. Okay, that's number 2. Okay, number 2. Number 2. Okay. And number 2, now 2 is rearranged. So you want to start out with the carbocation that you had, and then you want to rearrange that carbocation, and then that's where you're going to add the water. So in the textbook, I think it was the last chapter or the last section that I had in the reading assignment, it said additions with carbocation rearrangements. And so you want to follow all the same rules that we had from before with those rearrangements. And the other thing you're going to have to do with this is you're going to have to be able to not only write the products of the reaction, but you're also going to have to be able to write the mechanisms. So if you can write the products, we can always work backwards to the mechanisms. Okay, so for instance, let me show you how to do that in this one. But my question number 1, I'm adding H plus H2O. So what am I adding? What is my final product going to have? What's going to be attached to a double bond? An H and what did you show me? OH. So question number 1, what am I adding? An H and an OH. How am I adding it? Markovnikov? We're not into anti-Markovnikov yet, so in this case it's Markovnikov. I didn't ask for a stereochemistry because I guess we're making a chiral center, but we're only making one chiral center, so we would get a racemic mixture. So I need to add H and OH. For the major product, I need to add H and OH Markovnikov across the double bond. Okay, so that means that I would have the H added here, and the OH would be there. Okay. So can I work backwards here? Let's work forwards. So what am I doing? I'm adding H plus to the double bond. So we show the arrow to the H plus. Where's the H plus adding? To the carbon that has the most hydrogens, which in this case is the primary hydrogen, which puts the carbocation there. Then my nucleophile comes in, my H2O comes in. Just like any other SN1 reaction, the water is going to come in and add to that carbocation, which means I'm going to end up with my oxonium ion. And then what's the final step in terms of the oxonium ion? Lose H plus to then give me the final product. Okay. So again, from the carbocation on, it's just an SN1 mechanism, which is fine if you have your SN1 mechanisms under control. If you have forgotten about them since the last exam, you need to find them again and put them back in here, because that's all these mechanisms, at least initially, that's all they're going to be. Then when we're doing a carbocation, then when I said with rearrangement. So when I said with rearrangement, we're going to start with the carbocation we formed, which is going to be this one. people, or when I did this morning, people were like, well, where should I rearrange? How should I rearrange the carbocation? Same rules as before. This is the alpha carbon. I know we're doing substitution with it, but still, that's the alpha carbon. I can switch, or I can migrate, or I can shift from a beta carbon. That means I could shift that, or I could shift that. We're still not going to shift the entire ring, and that wouldn't do anything anyway. So which hydrogen am I going to shift? The one that gives me the more stable carbocation. One on the left or one on the right? The one on the left. If I shift the one on the right, what happens? Primary carbocation. Definitely not more stable. So I would shift this one over. And so if I do that hydride shift, I'm going to end up with the plus charge there. And then the hydrogen will move to the secondary carbon. And what happens next? Add your water, lose your proton, and you'll get the final product. So these reactions can undergo carbocation rearrangements, just like SN1s can, just like E1s can.
What happened to the hydrogen?
It's still there.
Like the one that we added to get rid of the double bond?
It's still there. Which one is it? Doesn't matter. It's still there. So you can have carbocation rearrangements. The rules are just like before. I got to tell you when to shift, and you can only shift once. So if I would have said, oh, that's a carbocation that results in a shift, the problem there is that carbocation resulted from two shifts. That violates rule number 1 that says only one shift. And that violates rule number 2 because I went from a tertiary to a secondary. I did not go to a more stable one. So you only get one shift. That's got to be to a more stable one. And I have to tell you when to do that. Again, I could do that by simply saying write the rearranged product, or I could say here's the reactant, here's the product, show me the mechanism, and you've got to identify along the way, oh, I need to shift. All right, so that's H plus H2O, which is called hydration. So whenever you take a double bond and you add to it H plus H2O, you end up forming the alcohol and H plus. That is hydration. Now, anybody getting a sense of deja vu with the mechanism that we wrote to form the alcohol, the one on this slide? As we were going through here, we formed the alcohol. Anybody get a sense that, wait, that looks familiar? Why does it look familiar? We've done it before in a different way. How did we do it before? This is hydration. Dehydration. What did we do when we did dehydration? We added H plus to the alcohol and went backwards to form the oxonium ion. And then what happened? It left to form the carbocation. And then what did we lose? A beta hydrogen to give us the double bond. Except the problem here is that if I took that alcohol and said, oh, I'm just going to reverse the process, I wouldn't get the same double bond, because the double bond would have to go in the most stable position. So it's reversible, but sometimes doesn't always give you the same alkene that you started with. And these are all equilibrium. This is all kind of an equilibrium reaction. So hydration, dehydration, same mechanism, just in reverse. All right. Everybody kind of with me? All right, then the last one is, what if I took that same molecule and I added H plus, I add H plus and methanol. What would be my major unrearranged product? What would it look like? I see a K. I have no idea where the K came from. Okay. Oh, I know where the K came from. That's a C, not a K. It's not some special C. Okay. Okay. Now, I have two editorial comments on these problems, given the last exam. So I see both of these answers. And then I see one without an H. So editorial number one. The bond has to go from this carbon to the actual atom that it's attached to, which is going to be the oxygen. Okay, so don't draw that bond. Number two, should the H be there or not? I mean, it can be, I suppose. But if the H is going to be there, then what else needs to be there? A positive charge on the oxygen. But what's going to happen to that? What's going to happen to this molecule? I'm going to end up losing H plus to form this. Okay. So we have our third reaction of the day. And again, if you take a look at this and you go back, look at your notes again after class, which is I strongly recommend. Maybe start the chart on how does it add, what are you adding, how are you adding it, how are you adding it. They're really similar. I mean, all the mechanisms are pretty much the same. So we want to make sure that it's an OCH3. Remember this. HOH reacts like ROH. Only in this case, what am I adding? An H and an OR group. How? Markovnikov. How? 50% cis-trans. Okay. All right, I do have a graded problem for you for Friday. I will post that when I get upstairs. It's going to basically be an E2 reaction, writing on a cyclohexane ring with an alkyl halide, write the products of E1, NH2 minus, tertiary butoxide minus. So you're just going to write the products of those reactions, and that's going to be your graded problem assignment for Friday. All right, just throw everything in the up front here.
Can I email you a picture because I have my orientation at Ohio State on Friday, so
Yeah.
I won't be here.
That's fine.
So they're not over there.
It doesn't matter whether it's there or not.
Okay, I just wanted to.
It's assumed. What?
Slides are gonna put the problem.
No, I'll post it separate.
I was thinking like and
Number 7?
yeah,
Number 7 was mismarked on the key.
so it's supposed to be R.
Yeah, I'm gonna go back and regrade everybody's.
Gotcha. Okay.
Somebody pointed that out, I just haven't had time.